In this example, we are going to do a few different cases applying the Pythagorean theorem. As a reminder, the Pythagorean theorem applies for a right triangle and is the equation a squared plus b squared equals c squared. In that equation, recall that a and b are referring to the two small sides of the right triangle, and c refers to the one long side known as the hypotenuse. Using this concept, we're going to find the missing side, the value of x, for each of the following triangles using the Pythagorean theorem. Do note that each triangle may not be drawn to scale. For this first example, we have a right triangle designated by the box on this one corner angle measure, and we have two side lengths known as 3 and 4. We are going to solve for x, and in this case, x is the side length that is across from our right angle measure. That means that x is known as the hypotenuse in this case. If I apply the Pythagorean theorem, a squared plus b squared equals c squared, I have to make sure that x in this case is denoted as the hypotenuse side and is in place for a c. A and b are the two small side lengths, and it does not matter which is which. I will choose a to be 3, and I will choose b to be 4. Therefore, I have 3 squared plus 4 squared equals x squared. 3 squared is 9. 4 squared is 16. That will equal x squared. Therefore, 9 and 16 make 25. That is equal to x squared. Since we are solving for x, we need to do one more step to get x by itself. That is taking a square root of both sides. If I do that, I have my final solution that x is equal to 5. So that is my first answer. Note that in this triangle, we have 3 side lengths that are all nice whole numbers. We have 2 small side lengths of 3 and 4 and a hypotenuse of 5. This is not going to happen all the time. This is actually less likely to occur. However, when it does happen, we take note of it because this is a pretty common triangle that you will see in Math 1060. We also sometimes refer to these special triangles that have 3 nice whole numbers as Pythagorean triples, or 3 numbers that fit the Pythagorean theorem that are all whole numbers. In this case, we say that the triangle, or the triple 3, 4, 5, refers to a triangle with 2 small side lengths of 3 and 4 and a hypotenuse side of 5. Again, this is not going to happen all the time. If you have 2 whole numbers, it does not necessarily mean that the third side length is also going to be a whole number. But when it does happen, we do take note of it. In the second case here, we have another right triangle. However, the value that we're trying to solve for x is next to or adjacent to this angle measure. So we're not trying to solve for the hypotenuse this time. Therefore, when I use a squared plus b squared equals c squared, I'm not going to plug in x into c squared here. I'm going to plug 13 in for c, and I'm going to plug x into either a or b. I will choose a. So in this case, we're trying to solve for one of the small side lengths. At minimum, we know at least that this side length has to be smaller than the hypotenuse. Remember, the hypotenuse is defined as the longest side length. So I know that x has to be smaller than 13. If I try to solve for x here, I will get x squared plus 5 squared is 25, and 13 squared is 169. If I subtract 25 from both sides, I will get x squared is equal to 144. And just like the previous problem, I could take the square root to both sides. This actually does come out as a nice number. X is equal to 12. This means that we have discovered yet another Pythagorean triple. We would define this triple from smallest side to longest side as a 5, 12, 13 triangle. So another nice Pythagorean triple to keep in mind. For the third example, note again that the side length that we're trying to solve is next to our angle measure of 90 degrees. That means that the side length that we're trying to solve for x is not the hypotenuse. 15 is the hypotenuse here. So when I use a squared plus b squared equals c squared, I will plug 15 in for c and plug x into either a or b. I used x as a last time, I'll use x as b this time, although it does not matter. If I solve through this, 12 squared is 144, and 15 squared is 225. If we subtract 144 from both sides, we will get x squared is equal to 81. And therefore, taking a square root of both sides yet again, we get the principal root that x is equal to positive 9. However, in this case, even though we got 3 whole numbers yet again, I'm not going to say that this is another Pythagorean triple. The reason for this is if you look at the 3 numbers we have, 9, 12, 15, all 3 of those numbers have one common factor, that common factor being 3. 3 divides into 9, 3 divides into 12, and 3 also divides into 15. If you do happen to divide all 3 of my side lengths here by 3, 9 divided by 3 will give you 3, 12 divided by 3 will give you 4, and 15 divided by 3 will give you 5. What this is a magnification or a similar triangle to the previous triangle that we defined, the 3, 4, 5 triangle. This 9, 12, 15 has the exact same shape as the 3, 4, 5 triangle. It is just a magnified version of it. For the last example here, we have 2 side lengths of 9 and 7, and the side length we're trying to solve for, just like the first example, is across from my right angle, meaning that this is the hypotenuse side. So, using the Pythagorean theorem, a squared plus b squared equals c squared, we get here that x I'll plug in for c, and 9 and 7 I'll plug in for a and b respectively. Solving through with that, 9 squared is 81, and 7 squared is 49. 81 plus 49 will give you 130. And just like in the previous cases, we will need to take a square root to find our final results. However, unlike the previous ones, if you do take the square root of this value, you are not going to get a nice whole number. Again, this is going to happen more often than the situations where we got a nice whole number. In those cases where we got a nice whole number, those are called Pythagorean triples, and they're very convenient to work with. But most mathematics in real life is not convenient. So, if we do take the square root of both sides here, if you approximate your solution here, you will get that x is approximately 11.4018 if you round up accordingly.